So hello everyone, Morgan Jack, a pre-sales engineer at Multithreading Technologies, and Eloi Grodry, the IT and HPC manager of Multithreading Technologies, is with me for presenting the webinar. The aim of this presentation is to introduce you the capabilities of Actran for the distributed computation. So you will see that for improving the simulation efficiency, Actran offers several methods for using all the resources available on your computer. And these methods are really easy to use and are feasible even on a laptop. To conclude, there will be a wrap-up. It will be the opportunity for you to have answers to your questions. So about the agenda of today, above all, I will present you very briefly our software Actran and what are its strengths for optimizing the acoustic simulation. Then Eloi will talk about the capabilities of Actran for distributed computation, and I will illustrate this on a simple example, namely the acoustic radiation of a gearbox with comparison of computational times. Finally, Eloi will perform a live demonstration, and it will be the time for the conclusions and the wrap-up. So what is Actran? Actran is a software for performing acoustic simulation and is developed by the company Multithreading Technologies, FFT in short, which is the acoustic business unit of MST. About Actran, our software is very general. It's a very general purpose acoustic tool. And the backbone of our solution is Actran Acoustics for studying acoustic wave propagation inside a fluid, then for taking into account structural components implied in the noise generation or in its propagation or even its attenuation. It is necessary to update to Actran vibro-acoustics. And for addressing trim car body, the module Actran for Nastran combines the best of the two worlds. Actran is used for modeling the cavity and the porous material inside a cabin, and Nastran to solve the structural behavior of the car body. Actran also gets all required physics for studying flow-induced noise with its module Actran aero-acoustics. And finally, Actran TM and DGM are mainly focused on representing the noise source of aircraft engines, even if Actran DGM also is very adapted for studying the sound radiation within very large domains. So that sums up the physical problems that can be tackled with Actran. Of course, a graphical user interface, Actran VI, allows to perform simulations very easily. Today, we will focus on Actran DMP, which allows significantly enhance the computation's efficiency thanks to the distributed computation. So let's see more generally how to optimize the simulation with Actran. Actran has significant assets for improving the acoustic simulation's efficiency. It starts with the pre-processing thanks to a dedicated GUI, the automatic meshing and the scripting ability that allows automating the entire pre-processing. Then for fastest calculations, Actran offers advanced symmetric boundary condition and distributed computations with parallelism and multithreading. Finally, about the post-processing, Actran gives a direct access to acoustic indicators, like the radiated power, the dissipated power in each layer of a multi-layer material, or transmission losses, TL in short. The software also displays results in classic units used in the industry like dB, dBA, third octave, band, and it gives a global noise value, namely the overall sound pressure level on the entire frequency range. Scripting capabilities can also be used for automating the post-processing. So today we will focus on how to decrease the computational time thanks to distributed computations. So now I leave the floor to Eloi that will give you an overview of what can be done with Actran in terms of distributed computation.
Yeah, so the first question to ask ourselves is, what is HPC and why does it matter? HPC is the acronym for High Performance Computing. It's the best way to do something in the most efficient and the fastest way. You need to know that HPC is not limited to huge clusters of computers that cost thousands of dollars or billions of dollars. We're not speaking about that today. Actually, the same key ingredients will be used no matter what the computer uses. You need a processor, you need memory, you need disk, but that's all about it. Today, even a basic laptop or a desktop comes with a multi-core processor. Even your smartphone got a multi-core processor. But let's focus on laptop, desktop, workstation, and servers. If you begin using all the cores available on your computer, then you will get much faster result from Actran. There are two most common ingredients in HPC. The first one is multithreading. Multithreading is about a team of threads that works together on a given task at the same time. They share the same memory space for the process. It means that each thread got access to the memory of the whole process to perform a computation. The second most common ingredient in HPC is MPI, the short for Message Passing Interface. MPI is a bit more difficult to understand, but it's quite easy to use. The idea here is that you get a team of processes, and not threads, that work together on different tasks. This task results from a distribution of the whole computation. And these processes communicate between each other using messages. Okay, so they don't use the same memory because they are different processes. So the idea of HPC is to speed up a computation and address larger and larger problems because it's the main simulation needs today. Just a bit of vocabulary before starting to explain what is done in Actran. Let's speak about a node. A node is any computing resource. So it's your laptop, your desktop, a workstation, a server on your cluster, and whatever. When we speak about intranode parallelism, we mean the MPI parallelism that is limited to a given node. It means that all the computation will be done on the same node. When we speak about extranode parallelism, it means that you will distribute your computation on several nodes, maybe on a cluster, maybe on two different computers that you have on your desk. And lastly, hybrid parallelism. The idea of hybrid parallelism is to take the advantages of multithreading and MPI parallelism, to use both features at the same time. So what we do basically in Actran is that we offer both the multithreading and the MPI parallelism capabilities. Multithreading is done inside a BLAS, with OpenMP as well, and with pthread. MPI parallelism is used all over the code when you need to do intranode or extranode parallelism. What you need to get today is that both functionalities can be used very easily. You can use a dedicated command line, and I think that Morgan will show this, or I will show you this later, and the graphical launcher as well. You don't need to be an IT expert. Actually, when you install Actran, you automatically install every ingredient that allows you to use multithreading and MPI parallelism. There is no need to set up anything. You just need to install Actran, then you can launch your first parallel computation. There are some other facilities that we embedded into Actran. The most important for me right now is that Actran will monitor your job. It will allow us to help you diagnose any issue that you might have if you try to do something and you don't have good results. Okay, I will let Morgan go on with the presentation.
Thank you, Eloi. So this capacity of Actran to address distributed computations can be used for reducing the computational time on small calculation units, like a workstation or even a laptop, by taking advantage of all the computational resources. But it is also very adapted for running computations on large clusters. First, I will first mainly talk about distributed computations that are adapted for small calculation units, and then for large clusters.
Just one point, Morgan, when we say large cluster, we don't mean this kind of large clusters, do we? By large cluster, we mean like 10 nodes, 20 nodes, whatever the number of nodes that you have.
Yeah. So two methods in Actran allow you to reduce the computational time, whether for laptops or clusters. There is many methods in Actran, but these two methods are especially adapted for small computational units. It is the multithreading and the frequency parallelism. So I have tried to figure out a simple definition of these methods. Then I will give you some examples for a better understanding. So in 2 words, the multithreading is when all frequencies are computed on the same process using several threads, which means several cores. And the frequency parallelism is when several frequencies are computed at the same time, distributed on different processes. So now let's see a concrete example. The first question you might have is when to use multithreading. So let's say you have a laptop, a basic one, with 4 GB of RAM and 4 cores. The sequential computation, which means not distributed computation, requires 4 GB of RAM. So you get 4 GB of RAM, and this computation already uses 3 GB, which means more than the half of the available memory. Therefore, frequency parallelism cannot be used efficiently in this case. But this computation only uses 1 core, and your computers has 4 cores. So 3 cores are not involved currently in the computation. You can use, in fact, these 3 remaining cores thanks to the multithreading to speed up the computational time. It means you have now 4 cores that are used at the same time for computing 1 frequency, like 4 people that are on the same bike. This type of distributed computation will act especially on the factorization step. So that was for the multithreading. Now, when to use the frequency parallelism. You have the same laptop at your disposal, but this time, the computation in sequential mode requires 1.5 GB of RAM instead of 3 GB previously. What does it change? Well, now less than half of the available memory is used, so the frequency parallelism can be used efficiently. So you have now a frequency parallelism on 2 processes. So 2 processes are running at the same time. Each of them are using 1 core and 1.5 GB of RAM and are solving a different frequency. Therefore, the total RAM consumption is now of 3 GB. Sorry. Now we can also remark that 3 cores are still available, so that we can also use the multithreading together with the frequency parallelism to speed up further the computation. Finally, you have 2 processes that are running in parallel, and each of them is solving the problem at a different frequency using 2 cores. So the image is 2 bikes with 2 people on each bike. So all the 4 cores of your laptop are used for the computation. This is an example of frequency parallelism on 2 processes, but with more memory available on your computer, you will have been able, of course, to apply a frequency parallelism on more processes than 2. So now let's see an example, the case of a gearbox. I have computed on a laptop 2 days ago. The acoustic radiation of the gearbox has been computed, and I will show you the results in terms of computational time for different computational methods. So the gearbox is part of a more complex system that involves gears and belts and the dynamic behavior, the movement of each part of this gearbox, is modeled by Adams. Then MSc Actran is used for computing the vibrations, and finally Actran is used for computing efficiently the radiated noise. The laptop I have used for this test contains a processor Intel Core i7 at 2.4 GHz, 4 cores, and 8 GB of RAM. I have run the computation at 6 frequencies and without any parallelism or multithreading, and it took a little bit more than 11 minutes. Then I consider a base of 100 so that the comparisons are easier to understand. The value 100 corresponds, in fact, to the computational time in sequential modes, namely 11 minutes and 44 seconds. First, using the multithreading, I succeed in decreasing the computational time from 100 to 62 with 2 threads, namely 2 cores. And using all the 4 cores for accelerating the computation, I fell to 45, which means less than the half of the initial computational time. On the other side, using the frequency parallelism on 2 processes, it allows me to decrease the calculation time to 55. And by combining it with the multithreading, I fell to 36. So on this laptop, the better configuration is to use a frequency parallelism on 2 processes, and then to have each of these processes calculated by 2 cores to reach almost 1/3 of the initial computational time. For going further, I can talk about other parallelism capabilities available in Actran. First, for large vibro-acoustic computations, a matrix or a domain parallelism can be used by running Actran simulations, for example, on 30 different nodes that have their own RAM memory. Then, for induct propagation, and more particularly for turbomachinery noise, namely the computation of the noise that goes out of an air intake, an exhaust, or a bypass, duct modes can be heavily involved in the source modeling. In that case, the load case parallelism and the axisymmetric order parallelism can be very helpful for reducing the time necessary for carrying out the simulation. Finally, to take advantage of very large computational systems, dual parallelism are available in Actran, which means the matrix or the domain parallelism can be combined, for example, with the frequency parallelism. The load case parallelism can be combined with the axisymmetric order parallelism, and so on and so on. Now it's the time for a live demo, and I once again give the floor to Edouard.
Okay, thanks, Morgan.
You're welcome.
So let's say that you already get your model in place on your computer, and Actran 15 has been installed. You will right-click on the model and then launch with Actran 15. You will get the graphical launcher, and if you look at the launcher, you will see 2 different kind of frame. First one is about multithreading, that allows you to select the number of threads that you can use on your computer. Okay, and the second frame is about intranet parallelism, where you can select the parallelism that you can use.
I think that with the WebEx, it's not possible.
Okay.
Appuie en bas à gauche.
I'm the IT guy, but I don't know how to use the trackpad. Okay, so let's say that for the first computation, we're gonna try to use. We got 4 threads, and we got like 2 threads, and then we will launch the computation using.
En bas à gauche.
3 GB of RAM. I'm gonna launch the computation and pop up the task manager. Okay, then the computation is running. Oh, cannot see this. If you look at the CPU usage right now, you see that we are above half the CPU resources for this computation because we are not in a multithreaded part of Actran. This is why at some point MPI parallelism can be much more faster than only multithreading. Then when we'll be at the factorization stage, you will see that the CPU usage will increase up to the maximal capacity of the computer. Mm-hmm.
Okay, so is the assembling of the currently the assembling of the matrix?
The matrix that's gonna be solved for the factorization.
And now it's the matrix.
And if you look at the CPU usage, it's increasing by a factor of 2 because we are using 2 threads. Okay. Well, I'm not going to let the computation finish because I think it will take about 4 times if I remember correctly. Okay, I killed the process just to show you that you could have been using MPI parallelism as well. So for this model, the frequency parallelism is the one that you want to use. I can, of course, use multithreading, but then on this computer, I'm just going to show you the frequency parallelism right now. So I select frequency for the type of parallelism, and then 2 processor. Then I launch. If you look at the CPU usage, you will see that we got much higher number right at the beginning of the computation until the end, actually, because there are 2 processes that are using 2 different cores to run the computation. I think that you got like 6 frequencies to solve.
Yes, right.
Then it means that we have 3 frequencies on each process that are going to be solved. Okay, so the expected time of computation is about the half of the sequential computation time.
Yeah, we can see maybe that the two processors in the I show with my mouse in the middle are involved in the frequency in one frequency computation each of them, and other cores is for Windows tasks. So these 2 cores are involved in the computation.
Yep.
And at their maximum. Okay.
Mm-hmm.
Okay. So thank you, Eloi. I'm coming back to the PowerPoint. So to conclude, parallel computations with Actran have been introduced, and running simulation using frequency parallelism and multithreading is possible with Actran, which allows to significantly reduce the calculation times, even on small calculation units such as desktops or laptops. And more advanced options also exist to take advantage of large clusters, such as load case parallelism, matrix parallelism, or dual parallelism. The practical use of parallelism options available in Actran have been showcased during a live demo by Eloi. And finally, I encourage you to experience this option by yourself during the coming weeks by requesting the free trial. So thank you very much for your listening. So now it's time for the wrap up and for Q&A.